So hello everybody, can you hear me? Thank you, got it. So good afternoon everybody. So today is our first lectures on the power and machines. So welcome you all back to coming to the new semester, new year. And for these lectures, because as you know, there are situations, right, pandemics here. So all the lectures and tutorials will be continually, right, conducted online. So and you see here, so on this slide, so on the Monday, we have the lectures lasting about 2 hours, online. And Thursday, we have 1 hour tutorial sessions. We will talk about some examples explaining deeply about the contents we learned in lectures. About laboratory works, basically, we have taken the lab videos, and the videos will be uploaded onto the website in due course. So the links will be distributed to you, and when it is ready, optional face-to-face laboratory sessions will be available based on the requirements of some of the students. But we should follow the guidelines published by the government. So sometimes government does not allow the indoor classes with persons with the numbers of persons many than 10 or 7 or something like that. So we didn't know at this moment. So we just say that probably in late of the March and even in the late of the February. So some students may like to make up the laboratory works. We can arrange all that, subject to the applications of the students and also subject to the situations or policies of the government published at that moment. So the lab coordinators, Dr. Hilda, so we'll write to you in due course about the specific arrangement. About the contents of these lectures, actually this is the continuations of the last semester's electric technologies. So that course is the fundamentals for this course. So in this course, we will have 4 chapters to learn, mainly on the power machines. The first one, of course, will be the transformer, which including the single-phase transformer and the 3-phase transformers. So we have already learned about the single-phase transformers in last semester. So, but here today, we will have a very quick and a briefing on the single-phase transformer. Then we will come to the lectures on the 3-phase transformer, mainly focus on the explanations of the difference between the single-phase and the 3-phase transformers. So with the basic knowledge of single-phase AC and 3-phase AC systems. In chapter 2, so we will talk about one very typical electromechanical machines. So we choose the induction motors as the beginning, right? So because these motors be widely used in the buildings, and it is powerful, and it is principles very typical, which based on the inductions, electromagnetic induction functions. After that, we will talk about the generators. In the generators, we choose the synchronous generators. We have different type of generators, but we choose this one as the typical one to introduce to you the basic concepts of the generator and the principles of the generator. If you want to learn about the machines, you can read some reference books are recommended so that you can know more about the motors and the generators. Basically, the motor, generator, and transformer, they're okay, basic principles, as I just stated in last semester, very similar to each other's. Okay. Of course, I will focus on the difference between them. Chapter 4, we have a quick look at DC machines. We have various types of DC machines. Once again, we say DC machine because that the inputs for the DC motors and outputs from DC generators are DC, right? Are DC voltage. So we call it DC machines. But actually, okay, inside the machine, the operation principle is still based on the AC. Okay, so we will focus on that. Anyway, so for each chapters, their linkage, their relationships, their differences, right? I will explain to you. For the materials, we have the teacher notes, okay, written in some of the statements about the definitions, concepts of different definitions of the concepts and the principles in general. We also have the PowerPoints, right? We prepared for lectures and tutorials, but PowerPoints is not right. So include all the contents in the teacher notes. Okay, so just giving some of the focuses, the highlights of it. So before coming to the lectures, I strongly recommend you that to read the teacher notes first, then have a look at the PowerPoints. Then you can catch up the points, okay, when I'm talking about some things. In addition to the teacher notes and PowerPoints, I also combined exercise books. So in the exercise books, okay, there we have the questions, okay, with the answers. We have some problems with the solutions. We have some of the past paper examination questions with the reference solutions there for your self-studies. Of course, for some of the typical questions there, I will also deliver it during the tutorial sessions if we have enough times. So anyway, so with these three types of materials, I believe that you all can get good knowledge on the power and machines. Of course, due to the time limitations, we cannot explain to you very details about each of the principles. Okay, assessment. So here I will tell you about assessment. Assessment, very similar to the previous assessment. We have the take-home examination marks. So this semester we do have the take-home examination. Okay, not online examination and not on-campus examination. So the take-home examination typically taken 1 day. You are required to finish of it. So towards the final subject marks, taken 60% final examination, and continuous assessment marks, so share 40% towards the final subject marks. So the consistent assessment including 2 assignments. So the 2 assignments together share 25%, and the laboratory report, which share 15%. I strongly recommend that you try your best to complete all this continuous and final examination assessment. Because in previous semesters we do have some students that do not submit the assignment. As a result, they fail the subject. We do have, the third point is that passing the subject needs to get a pass grade for both the examination and continuous assessment. This obviously, so although we say that 40% of the continuous assessment, 60% of the final examinations, but if you failed in final examinations, no matter which grade you obtain for the continuous assessment, for example, in the continuous assessment, you got A+, but in the final examinations, you got fail, that the subject will fail. Similarly, if you fail in the continuous assessment, that's difficult to fail the continuous assessment because we have 4 or 3 components, right? Assignment 1, assignment 2, and the laboratory report. Okay, but still, may have, right, some students have failure in the assessment, right, continuous assessment. So if you fail in continuous assessment, you will also fail in the right final examinations. So no reassessment, that means not late assessment, okay, unless you have solid, right, okay, you have some of special reasons, for example, sickness with the doctor's certificates, or some very special, right, incidents or something that that you cannot attend the examinations on time. So we may arrange some of the real assessment or late assessment, subject to the approvals of the department, right, board of examiners. Okay, so this is the principles about the assessment. So I would like to tell you all in advance. Okay, so here is some of the possible, right, reference books that you may find in the libraries. So of course, not exactly the same names, but basically, there are several books talking about the electric machines. So the first one, as you see here, is Electrical Machinery Fundamentals. And also we have the electrical power engineering, okay? So we have the electric power technology, basic electrical and electronic engineering. So we supply with you the study guides. So 3-phase transformers, induction motors, synchronous generators, direct current machines. Actually, all these materials has been already posted on the Blackboard. You can download or print out based on your personal favorite. Okay, so for the laboratories, we arranged 2 experiments because we cannot so arrange much more. So the laboratory data sheet of the instructions of the laboratory sheet will be distributed to you by the coordinators. Okay, so we have the electrical examination, electric experiments 03. So testing of polyphase induction motors, including single-phase conditions. We have the electrical experiments number 7, polyphase transformer phasors diagrams and equivalent circuit. Okay, so this will be posted on the Blackboard of the website. Okay, maybe on the YouTube or on the OneDrives of the university. Okay, so generally you are required to read or watch carefully both videos of the laboratory works, and at the end you are required to submit one formal report for one of the laboratory jobs. If you choose to take face-to-face labs, if it is possible, if it is occurred, then you are required to submit 2 logbooks of both laboratory works and 1 formal reports. Here we just would like to have an overview of the electric subject arrangements. So why we have so many electric subjects? What's their relationship between them? Actually, as you can see from the student's handbook, so for each program, they have their own visions and program structures. So actually, our subject arrangement is mapping with the program's purpose, objectives. Okay, for each of the subjects, we have their own intended subject outcomes. Okay, so we have to arrange our teaching and learning methods aligned with the intended subject outcomes. And also we should arrange the assessments that to reflect the intended subject outcomes. Okay, here, so since that you have come into the year 2, okay, so you should know that these programs has their objectives. For the Bachelor of Engineering Building Service Engineer, one of the objectives is that the program designed to teach the students design analysis of the building electric systems on the basis of understanding of the function and the principles of the building electric services. So this is the one big objectives of these programs that attracting the students come here. So we based on this objectives of the programs, we arranged several subjects. So the typical electric subjects here show that the BSE 21-22 and the BSE 21-23 and the BSE 1323, 31-23 and BSE final year subjects, research projects 47-23. Last semester you learn about the BSE 21-22. Okay, so for this semester, we learn about the BSE 21-23, which is the power and machines, which is in the basis of the BSE 21-22. So for these subjects, the subject objectives is that to teach you to understand the functions and principles of rotating machines and power equipments in building electric services. Okay, so rotating machines, we have various types of rotating machines, and we're types of the power distribution and usage equipments. So based on these objectives, we have arranged 3 topics. The first one is the power distribution machines. That's the transformers. The second one is the AC power machines, which including the motors and the generators, which use or output AC powers. And then the DC machines. We have the DC, motors, DC generators that use the DC voltage or output the DC voltage. Okay, so we have 3 big, parts. And specifically, the intended subject outcomes. So after you learn about the subjects, we expect that you are able to model electric machines and equipments and to use the model in problem solving. So that's why for each of the machines we learned in these lectures, you are required to be able to get models of the machines in terms of the electric equivalent circuit. Okay, so once you got the electric equivalent circuit, to describe the machines with the different electric parameters, such as the voltage, current, impedance, the impedance including the capacitance, the inductance, and the resistance. Then you can analyze the machines, the performance in terms of the input or output voltage current, input output energies, internal energy losses, the machine's output efficiencies, the machine's the internal core losses and copper losses, etc. And also the electromechanical machines energy conversion efficiencies, and so on. Okay, so the motor is very important issues, which will be frequently delivered or taught in the tutorial and during lectures. The second, right, intended subject outcomes is that after you learn about these subjects, you are expected to be capable of recognizing, analyzing the operating modes of machines and equipment as part of building electric services systems. When we talk about the machines, you will find that, so for rotary machines, they may have different, right, working operating modes. In the, for examples, so in your homes, you may use in the air conditioner systems, which is driven with the motors. You may have the small fans. You may have the washing machines. You may have the refrigerators. You may have the heaters. You have the vacuums. So all these, right, actually using electricity and using the motors. So the motors, you found that they're working at different mode. Will have different performance with different power consumption modes. Understanding their operating modes and know how to analyze their performance so that you can optimize the design of the machines, or you can got the if the machines got failure, you can know how to correct it or how to repair it. So this is the two very specific intended subject outcomes. All the lectures and tutorials and assessment will be arranged around these two intended subject outcomes. Of course, for each of the sessions of the courses, we have their own focus. The lectures, we will not talk in detail of examples, but we will focus on the principles and the systems models of different rotary machines, So we will talk about how to get the equivalent circuit of the transformers, of the motors, of the generators. And also, we'll introduce to you how to analyze the performance of the machines based on the motors. Of course, the students can raise questions during the lectures. You can write down, but here, because we do not write the face-to-face lectures, so you cannot ask me questions in face so that I can explain to you in face. But you can write down that questions immediately in the chat box. I also can write verbally or orally reply to your questions. So in the tutorials, so we will give you some of the real problems in designing and testing of the machines. So we suppose that we have done some testings. We got some of the data from the machines testing, and we get to analyze the data. Or we, based on the testing of the machines, we try to figure out or draw the equivalent circuit of the machines, and so that we can analyze the performance of the machines based on testing data. Of course, we have several questions we will explain to you based on that real problems during the tutorials. We will give you as much as we can the examples, but subject to times. Lab works, unfortunately, probably that most of the students will doing the labs while watching the videos online. So you cannot, maybe you cannot come to the labs to touch the machines. Training, so-called training now is the paper training. We suppose that probably in the coming semester, for example, in the fall of this year, or the summer of this year, or even the next year, if you have a chance, to come to the campus, you can ask us to make up some of the lab experiments. So lastly, we have the exercise. So we have examples, very detailed examples, and questions, past exam questions. The exercise already posted on the Blackboard, the books you can download, okay, to read it, okay, in advance. Okay, so this is the assessment, right? So of course, right, the examination cannot be right close to the book, right? So okay, here is just the simple drawings that are showing you that. So the PowerPoint or the teaching notes, how the PowerPoint and teaching notes be arranged. So before you learn about chapters, I hope you that understanding the linkage between each right slide of it. So generally, so the teaching notes, including the lecture PowerPoints, has been organized in a way that first we show you the machines, the basic constructions, okay, the basic constructions. Then based on the structures, okay, so we're talking about the principles. We're talking about the functions of each parts of the machines. Okay, so based on the principles, we further to introduce to you about the power flows inside the machines. Okay, inside the machines. So based on the principles, based on the power flows, based on our understandings of power issues, and also the basic concepts, the voltage, current, the impedance of the electricity. So we then can find out, define the machines, okay, circuit, okay, parameters. Okay, so this is the modeling of the machines. So using the electric terminologies to describe mechanical electro machines. Also here we may involve some of the mechanical parameters also. Okay, although we do not talk about mechanical issues in last semesters. Okay, but while we talking about the rotating machines here, I will try my best to also give you some of the concepts of the mechanical energy issues, because here we're talking about the electricity transfer to mechanical, okay, for the motors and for the generators that we transfer the mechanical energies into the electricities. So how to describe electrical powers, how to describe the mechanical powers, what's their relationships. So we have to learn about that. So that's the parameters. Okay. So then, so we have the principles, we have the motors of the machines. Okay. So in the tutorials, okay, so we will fix on the motor circuit. We suppose that we have the testings. Okay. Suppose we have the testings. So we have the designs of machines. Then we analyze the features of the machines based on the motors and based on the testing results, based on the testing data. We can, based on these questions to focus, okay, to study about the usage of the motors. And originally the labs, okay, the labs focus on the design of testing machines. Okay, then based on the data you obtained during the laboratories, you can analyze. Based on the motors, you can analyze or explain the features of the machines. That's our original design of the subjects. And for the assessment, okay, so we have the continuous assessment and final examination, okay, marks. For continuous assessment, once again, okay, so we have 50% about the principles, about the motors of the machines. Okay, we have the 50% about the modelings and testing and the designs. Okay, so the tutorial, of course, will focus on the basic analysis of the machine's performance. We do not talk so much about principles again. Okay, for the final examinations, of course, So the 70%, as I show here, 17% questions will focus on the modeling, feature analysis, design, and testing of the machines. And we still have 30% that the concepts or power principles or concepts, some of the specific right terms will also be examined during the final examination period. So which may require you to read some of the books, reference books, not simply to get the answers from the teacher notes, but you need to read some of the reference books to get more rich knowledge on the basic principles of the machines. Okay, so here we just take half an hour, have a briefing on the design of these subjects. Okay, so hope that you have a overview of these subjects at the beginning of this semesters. Okay, that's the end of the instructions of these subjects. So following this one, we come into the chapter 1, the transformers. Okay, so now we move on to the transformers. So okay, so take it easy. That actually last semesters in the electric technology, we have learned about the single phase transformer, its principle, its equivalent circuit, its testing and analysis. But to have a good connection to these subjects, we start with the single phase transformer first. Okay. First, let's have a quick revisions on the single phase transformers. So here is the contents. So we have the so-called different types of the single phase transformer. We talk about the operating principle, ideal transformer, practical transformer. For the practical transformer, we showed you how to write the voltage equations to represent the transformers circuits. And also we showed you how to draw the equivalent circuit and what's the phasor diagrams of the transformers. And we also showed you how to test the single phase transformers. We have various types of the testings. Typical one is the open circuit tests and short circuit tests, and on full load tests, and so on. We showed you how to analyze the efficiencies of a given transformers, how to estimate the so-called voltage regulations of a given transformers. Because we have a break, more than one month break. Some students may forgot the principles of the single phase transformer. They one subject over, so they threw away the knowledge to learn their subjects. Okay, so we learned that for the basically, so we have two types of transformer. One is the so-called core type transformer. So the other one is share type transformer. So the core type transformer, as shown here, that means that both the primary coils and the secondary coils share the same cores. So they close, closely to each other. As a result, the mechanical force torques, produced by the interactions between the magnetic field on the primary and magnetic field on the secondary, okay, be smallized, right? Be very minimalized, very small, okay, because their distance between the two coils is smaller. With the same force, the torque is small. Okay, torque is small. So they are strong to the big current. They are strong to the big current. However, they are weak to high voltage. Okay, because they are small, close to each other. Okay, so generally speaking, that for the core type transformers, it is always be used in the gravity centers of the powers. That means where we use big powers with big currents, but voltage is not so high. Okay, so because it is weak to insulations between the primary and secondary. And this is obviously okay, but for the shear type transformers, as you see here, that the primary and the secondary, primary coils and the secondary coils, they are on the same core, but they're separate to two sides of the core. So they have a big difference between each other. So you can imagine when there is magnetic field on the primary, magnetic field on the secondary due to the currents, then the magnetic field in primary and secondary, we have interactions between each other. So this interaction is a kind of the strong mechanical force. Okay, so this mechanical force, while distance interacts to two coils, produce so-called torques. Okay, so making the coils, making the two arms, try to move. So this will causes some of the mechanical damage when the current too big. So you can imagine, so this type of transformer is weak to big currents. So if you have big currents, big mechanical force, and big torques that try to make this cores, try to make this core to move. Okay, so that produce some mechanical movements, vibrations. Okay, so this vibration, of course, will cause some of the damage to the machines, or derate the machine's performance. However, because the big space between the primary and the secondary, so this kind of machines is strong to high voltage. Okay, so it is weak, right, to the high currents, weak in case of short circuit, but strong in high voltage. Okay, so that's two types of transformers, but in practice depends on the design. So largely speaking, we have two types. So in practice, we may have more detailed, subtypes. Okay, so this slide actually showing you the basic principles of the transformers, which based on the Lenz's law, which is actually the induction. So we have a quick look at the principle, taking a revision. So suppose we have the primary coils, we say the V, primary with a primary current IP with the turn number NP here. And wire the core here, IR core, on the second side, we have the second coilus, which has a 10 numbers, suppose NS, with a output current IS, voltage VS, with a load that has a resistance R, okay, resistance is secondary. Suppose that in the primary we have a current IP changing with times, okay. Then we have the magnetic field, okay, produced by this current changing with times. Suppose the cross-section area of the coilus is A here, and the flux density is B, and the change rate of the flux density is delta B over delta T. So this is the change rate. Okay. Okay. So as you know, that based on the Faraday's law, Lenz's law, okay. So the change, right? So the change rate of the B, okay, all currents with the turn numbers with the A, that's the change rate, okay, of the right flux linkage. Okay, flux linkage. Okay. Okay, so this actually is the, okay, so Lenz's law. So the induced voltage, the voltage applied is the inductions. That's okay, actually. So the voltage applied here used to overcome the inductions on the coilers. So the inductions on the coilers, okay, is the right d phi p is the total flux linkage, which is the turn numbers, is the areas of the cross-section area of the coilers, is the flux densities of it. This is the phi. Okay, so this is change rate. Okay, this is the change rate of the total linkage. Okay, so this is the induced voltage. So this is the Lenz's law, right? Lenz's law. Very basic laws. So why we have such a law? This is a natural right rules. No one knows it. So scientists find out this one. Okay, so the reasons behind it, no reasons. Okay, now you're understanding what's the scientists, right? They just find out some of the things like that. Okay, no reasons, no why. So do not ask, right? Anybody's why like this. This is facts. This is the reality. But also, what's the B? I don't know. This is the parameters that used to describe invisible force produced by the current. Okay, produced by current. It's in the black box. No one knows details about that. Okay, so that's the grounds of the so-called right. Okay, Faraday's law. Okay, so then we have the right primary induced right flux. So this flux with the same change rate coming into the secondary side. On the secondary side, we have no source here, but the secondary, due to the Faraday's law, due to the flux, okay, they receive the flux from the primary. interesting from the primary. So on the secondary, so they have the same flux density with the same cross-section area would call, with the same change rate of the flux density, but the turn number is different. So the total flux linkage to the secondary is different from the total flux linkage to the primary. So the difference comes here. So this is secondary. So the primary and the secondary, so when you write down the functions, or we say the equations, they're similar, but difference is that primary voltage is the source that we say the excitation side. So the voltage Vp excite the force or excite the magnetic field changing. So the magnetic field changing that through the coil come into the secondary. So the secondary coils receive the flux produced by primary and the induced voltage across the two coils. The induced voltage at the end of the two coils and end of the coil 2. So this voltage then is supplied to load here. So it is open. If it is open, you still have the voltage be here. Voltage be here. So as a result, looking at here, so because the flux linkage at the primary and flux linkage at secondary, so they proportional to their own turn numbers of coils. As a result, so the primary voltage and the secondary voltage, linked to the ratios of the primary turn numbers and secondary turn numbers. So this is the principles. So you can see here, so actually the basic things is so the basic things is this rather than this. This is just Vs over Vp equal to Ns over Np is a specialized solutions. But the basic things is, so is the issues here. Issues here. So there are change, right? So there are change of the primary secondary over the change of primary. If no change, right, there is no voltage outputs. So probably here, so we have the so-called transformer that we change in the currents. But in practice, maybe if you can changing the turn numbers, even making the turn numbers change with times, or making the cross-section area of the core change with times. You also have mechanical transformers. That means if you have a DC voltage and the voltage is very low, but you like making this voltage be higher, how can you do it? So first you can using moving coils to making the voltage be transferred into a high voltage. There again making the AC high voltage into a DC voltage, right? You can do that. Okay, you can do that. Or you can change the DC voltage into a AC first, then using a transformer, making the voltage be higher, and then making the high voltage AC to a high DC. You can do that. Anyway, induction, okay, transformer should get applicable to AC, or changing currents, or changing flux. That's the principles, very important principles, also applicable to the three-phase one. And in practice, that we have the transformer be used in power distributions at different points of the power transmission systems. Actually, power stations, we have the state-up right transformers, making the right generated powers, generated electricity from low voltage to high voltage. Then we using the transmission line, transfer the high voltage electricity into the city or into the homes. Then we using the step-down transformers to making the high voltage to a low voltage, so that we can use low voltage in homes or in the buildings. Okay, so the transformers generally mechanically have the core materials, as we just said, have the readings. So we have the primary and the secondary readings for single transformers. And between the two coils, we have the insulation materials. So the insulation materials may be the gas, may be a kind of the liquid, right, insulation materials. So special gas, or even the air, or some of the solid insulation materials. So we have the air, insulated transformers. We have the special gas, insulated transformers. We have the special oils or special liquid, insulated transformers. Or we have some of the solid material insulated transformers. So different types of insulation materials. Enclosures, generally the transformer enclosures is not coppers, it's not aluminums, it is always using the steel materials, cast steel materials, which serves as the core materials, which can enclose not just the transformer parts, but also the magnetic fields. Because the steel materials can attract the magnetic fields running inside of it. So that's why for the transformers, later for the motors, we're using the steel materials, iron materials, rather than the copper materials, rather than the other metal materials as enclosures. Now you understand? Do not use the coppers to use it, right? So we use the steel materials because, it is the magnetic materials that attracting the, or that enclose the magnetic field, making the magnetic field not leak into the air, making the magnetic field surrounded be minimized, minimized, so that all the magnetic field produced by current be inside the transformer rather than the around in the transformers. There is cooling systems inside the transformers, because that the transformer we're running in full load with big currents. So due to the internal resistance of the transformer's coils, there are some power losses. Also due to the resistance of the cores, so there are some core losses. So the core losses, the copper losses, so making the temperatures of the transformer as a whole be higher. So which generally be up to 70 or 80 degrees. So In the field, maybe you see a lot of the transformers in use, but do not touch of it. You do not think that the transformer is enclosed. The transformer is earth, so there's no electric shock issues on it. But there is hot temperatures on it. So if you touch of it, you get hurt, right? Get hurt. Also, the running motors, even a small motors, in homes, even the motors in laboratories, the surface may be high temperatures. Do not touch of it. Okay. Of course, right? Some of you may drives, so the car uses the motors, so the motor generate big heatings that you're using the waters to keep the temperatures of the motors be lower than 100%, 100 degrees. Okay, right? So if the waters can dry out, your cars will, right? Be in trouble. Okay, so in electric schematic, so you can use different symbols represent the transformers. Okay, so the transformers, so you can using symbols as we draw here in the right side of this slide. So using the dot, indicate the polarities of two sides. That means in the circuit, how to connect the transformers correctly. When you have an electric right schematics, so you should tell the engineers, tell the workers how to connect the transformers to priorities. So you should mark out which line, which wires should be connected to the positive side of the transformer. Of course, the positive or negative here is a relative issues, because it is applied to AC systems. So AC systems, the polarities change with times. So the positive here is just a sign, relatively positive, at one moment. So this is different, from the DC case. And also, in practice, the positive and negative has another meanings. One, as I just said, positive and negative in practice actually they change with times. So generally, the negative side more or less has been in the way to Earth or with protective wires bonded to it. So although the polarity, positive, negative, is a relative one in the AC systems, but for the transformer informer, so when we mark a negative mark, so this end, negative bar end, most likely to be earthed or to be bonded to the protective conductors. That's the difference. Although the voltage on it, in comparison with the another end, sometimes be higher, sometimes lower. That's the meaning of it. That's the difference of it. So here is just some of the expressions that describe the relationship between the two sides voltage and currents. Suppose that there is a so-called transformation ratio. For an ideal transformer, if we define a transformation ratio, so the primary equivalent turn numbers over the secondary turn numbers defined as the transformer ratio. Some special transformers, because the winding structures, it is difficult to determine the accurate turn numbers. So here, the turn numbers primary turn number secondary, okay, is the equivalent terms, which, right, we have some concepts, okay, in electric circuit, but as a matter of fact, sometimes it is quite difficult to say so the exact values of a given terms. So in most of the case, the ratios of the transformers, okay, roughly estimated based on the correct turn numbers, exactly based on the, okay, by testing. So the turn numbers here, so equivalent turn numbers, not exactly the same, right? But okay, in practice, by testing, we got this one. Okay, and so because you learned, right? So this one in okay, in written, in books, in notes, okay, but practice, okay, by testing. As a result, there is okay, ratios of the voltage between primary and secondary, both the instant values, instantaneous values, okay, time variations, and the root mean square values. So you know, for the AC systems, we have the instantaneous values, primary, instantaneous values, secondary, and root mean square values, primary, and root mean square values, secondary. The ratios depending on the transformation ratios. And here is the power conservation law. So basically, if there is no internal losses, the primary powers should equal to the secondary powers, right? Primary input power, secondary input power, output power should be the same, right? So they just pass through the transformers. So from this point of view, so we have the ratios between the primary and the secondary currents. Okay, that's different from the voltage. Okay, so how the voltage is produced based on the Lenz law, or we said Faraday's law. Faraday's law. And once we have the transformation ratio defined, and we suppose the powers input from primary and powers output from the secondary be the same, which is the power conservation law. Exactly speaking, here the power should be apparent powers. So primary apparent powers, secondary apparent powers should be the same. Okay. The P here is just represented the power, but here exact speaking should be the apparent powers. Okay, not the real powers. Okay, so apparent powers, real power should have the power factors here, right? So this is the ideal transformers. And in ideal transformers, we ignore the core losses, we ignore the resistive losses, we ignore leakage flux. Okay, so we have cycle transformer ratios. And in practice, because the coils we used with resistance. And also the coilers, the magnetic field produced by the current on the coilers has some leakage as a result. So the induced voltage not exactly depends on the total flux produced by the currents on the coil 1. And also related to the coil's resistance. The coil's self-produced flux. If you have another coil's close to it and also produce flux, that flux comes into the coils. Then the one coil's induced voltage depends not only on the flux produced by itself, but also depends on the flux comes from the other coils. So in the single-phase transformer, we have the so-called primary and secondary coils. If we check on the primary coils, as we show here, suppose the terminal voltage we use in the VP represented, and the primary itself currents BIP. Its resistance, this is the copper resistance of coils. Do not confuse this one with the core. So this is the wire's resistance. So then this is the resistive voltage drops on the coils. And the primary coil itself has flux linkage. So this flux linkage is due to the primary coil itself. So its change rate, as I just said at the primary slide. So this is the flux linkage changing due to the itself. And this is the flux linkage change comes to the secondary due to the mutual inductance. So the flux linkage here due to the self-inductance. Right into the flux law again. So here is the resistive voltage drops on the primary coils. This is the inductions, the self-inductions of the coil 1 due to the current coil 1. So this is the mutual inductions, the inductions due to the flux from the secondary, produced by the secondary currents. So the secondary currents with time changing, and there is a mutual inductance between the primary and the secondary. So self-inductance, mutual inductance, and self-resistance. Some students may, right? Related to NP. NP. This is the self-inductance. This is the mutual inductance. Okay, so in the you learned that how to express the inductance. The inductance proportional to the turn number square over the reluctance for self one. For the mutual one, so the producer is the N secondary. The receiver is N primary. So the producer secondary current with the turn numbers N secondary come to the primary receiver N primary. Induced voltage R primary. So this term the producer is the coil 1 primary current IP, and together with the primary turn numbers NP. Okay, receiver, so by the primary itself NP. Okay, then induced voltage on primary NP, right? So this is the resistive voltage drop on primary. They together overcome the terminal voltage of the primary applied to. Okay. So if you write this into one side using the Kirchhoff voltage law, so that's Vp minus Rp Ip and minus Lp dip dt minus M dis dt. Okay, the same thing. So this actually is based on the Kirchhoff voltage law for this circuit. Okay. Similarly, that for the secondary, so we have the Faraday's law. Okay, actually, so the secondary voltage terminal voltage, secondary residual voltage drops, secondary self-induced voltage due to the inductance, and the secondary induced voltage due to due to the primary mutual inductance. Okay, similarly, so this one secondary, producer is the secondary, receiver is the secondary. But here, so the induction, the flux, producer is the primary, receiver is the secondary. That's the difference. Okay. So this is the instantaneous values. We use in the concepts that the root mean square values for sine cosine currents. Then we can change this Faraday's law into a voltage equation like this. So the root mean square value primary voltage, root mean square values primary currents resistance, and root mean square primary currents self reactance, self inductance, angular frequency of the currents, and then so self inductance. This is the mutual inductance. The secondary root mean square currents. Similarly, for the secondary side, we have the secondary resistive voltage drops, secondary self-induced voltage, secondary mutual induced voltage. They are symmetric to each other. So remember, we have the self inductance corresponding to self reactance, inductance, reactance. Later on, we will have the leakage reactance. We have the mutual inductance, mutual reactance, and transformational ratios here. And I also showed you the little difference between the mutual and self. Mutual and self. Unlikely because when the PPTP change into the blackboard used for let's say maybe a PDF, so some of the fingers disappear. So anyway, here should be the equivalent circuit. Generally speaking, that for the equivalent circuit, and the secondary so we first have the definitions of the primary secondary. So we have the primary, okay, voltage. We have primary currents. We have primary resistance. Now here, so we have the primary leakage reactance. We have the primary magnetizing reactance. So we have the secondary leakage reactance. We have the secondary resistance. We have the secondary currents. We have secondary voltage. So here is the secondary magnetizing reactance. So in previous slide, okay, we have the self-inductance, self-reactance, and a mutual reactance. Self-reactance can be split into the leakage reactance plus the magnetizing reactance. Okay, so if the leakage is 0, then the magnetizing reactance is the self-reactance, right? So self-reactance equal to leakage reactance plus the magnetizing reactance. Okay, if leakage zero, then self-reactance equal to magnetizing reactance. So magnetizing reactance also related to an okay. While mutual reactance okay related okay. Now here, because some students may be confused with it. So in previous slide, we say the self-reactance equal to leakage reactance plus the magnetizing reactance. So here is the magnetizing reactance. If the leakage reactance is 0, then the self-reactance is the magnetizing reactance. So the magnetizing reactance also related to the n primary square for the primary side. On the other side, that's the mutual reactance, as I just explained to you. That related to the primary term numbers, secondary term numbers. Similarly, that's the for the secondary. We have very similar one. The secondary self equal to secondary leakage plus the secondary magnetizing. And the secondary magnetizing related to N secondary. So the mutual, the mutual, so square magnetizing primary times magnetizing secondary. So because the magnetizing, so the mutual one related to the magnetizing. So the mutual, because the mutual, why the mutual, right? We put in a places that easier understanding. So why the mutual one related to the primary and secondary? In such a way, the mutual square actually equal to the primary magnetizing times secondary magnetizing, and their relationships here. So ideal transformer, so the leakage can be ignored, right? That's the difference. So here we try to explain to you clearly the parameters we use in equivalent circuit transformers, because I found that some students make confusions in the last semesters in both the assignment and final examinations. They do have some confusions. Not all, but some students, they cannot distinguish between the mutual and the magnetizing. They have very confused explanations on the list of the parameters. They even do not convince themselves, write down some things I do not understand at all. So this is explanations of the specific parameters. In addition to this, differences between the parameters are right here. So we have two, we have the so-called core losses. So that's the core losses, parameters, which generally be written in parallel to the input side, So we have the core losses here. So we have a whole core losses in parallel to the two sides, but here we cannot connect them together because there is ratio issues. So XMP, XMS. Okay, their ratio, of course, will be, look at here, XMP. The XMP related to the NP, XMS related to the NS. Okay, so their ratio, okay, of course, depends on the NP over NS, right? NP over NS square. Okay, so then if you try to draw a equivalent circuit based on these parameters, you have to make in the right two side the voltage be same. Okay, voltage be same. And so this point be same. Look at here, because the XM1 over XM1, XMP over XM2 is NP square over NS square. That's A square minus A square. A square, right? So if you want to make this one be same as this one, you have making this side over A square. That's why we have A square. Okay. So as a result, okay, for all the impedance here, for the secondary, you can making the impedance over A square, so that here the same, and making the powers no change. So if you're making the voltage be down by A, the current must be up by A, and the impedance, leakage reactance, and resistance be done by A square. So okay, so you can refer to the primary, you can refer to secondary, or if you try to keep the secondary no change, you have to make in the XMP times certain factors to equal to XMS, so that voltage here be the same. Okay, so this is XMS, this XMP. So how to make this one be equal to this one? Then you can connect it together, equal to each one. So how to make them equal? Because this one. Okay, so you can, based on Seitel principle, can quickly draw the equivalent circuit. Once again, this is the original parameters of the primary and secondary. Here we're using the magnetizing reactance primary, magnetizing reactance secondary. To draw the equivalent circuit, you have to make in these 2 points has the same potentials. Looking at parameters XMS and XMP, if you try to refer to primary, that means primary parameters keeps no change. You change the secondary one so that the voltage and these 2 points the same. So a simple way is that looking at the XMS. So if you want to make in the XMS be same as XMP, so the XMS should be times by A square, because itself is NS square, while the MP is NP square. So you try to make this one be equal to this one. You have to times A square here. Similarly, when you times A square here, for all impedance times A square. So A square here, just like here, A square secondary, A square secondary. A square secondary. Meanwhile, so keep the powers no change. Because this is transformer, you're making the voltage here be up. Okay, so that means the secondary voltage here. So because original is must times by A, while the current be done by A, refer to primary. Similarly, if you try to refer to secondary, so you keep the secondary no change, changing the primary parameters. First, so making the primary parameters XMP equal to times something equal to XMS. So the parameter, of course, is XMP over A squared will be XMS. Similarly, so XP over A squared and RP over A squared, plus the secondary cells. That's the equivalent impedance resistance. And the current here must times A, and voltage here must over A, while the impedance over A squared, impedance over A squared, voltage over A, current times A, keep the powers the same. Under whatever transformations, under whatever changes, the powers keeps the same. So this is very easy to do. So with such a right thinking, you can easily draw the equivalent circuit for any machines, not just the transformers. So simply remember the equivalent circuit is not a good way. Understanding how to draw the equivalent circuit is more important. So anyway, so this serves as revisions. Hope that you have good understanding on the drawing of the equivalent circuit. So here we're showing you in practice how to for a circuit with transformers in to draw the equivalent circuit from one side to another side. For examples, if we have a generator with a generated voltage EG and a wire transmission systems with a impedance Z1 with a current R1 on it through a transformer, this transformer can be seen as an ideal transformer in series with other impedance. The transformer's impedance primary and secondary. Primary can be belong to the Z1, secondary can belong to the Z, Z3 and Z2 and so on. Anyway, so then we see how to making the equivalent circuit. First, we can refer to the primary. So when we refer to the primary, as we show here, so the current primary impedance voltage keeps no change. But the secondary side, so internal the transformer, there is a mutual reactance. So they have A square relations. So A over 1, this is a voltage relation. Voltage relation is A. Ratio is A. But the mutual reactance is A square. So mutual reactance is square. So for the impedance, should be A square issues. So refer to the primary. So the secondary impedance, all the secondary impedance, times by the transformation ratio A squared. All the voltage, as a result, times by a transformation ratio A. And all the currents divided by the transformation ratio A, so that the powers keeps the same. So very straightforward. When referred to secondary, so all the secondary impedance, voltage, current keeps no change, the values. But the primary, the voltage, all the primary voltage be done by a ratio A, and the impedance done by a ratio A squared, and the current up by a ratio A. Probably, so because the should be like this, should be like this, so that the power is the same. The others no change, right? No change. Of course, if we have voltage, the voltage keeps no change. Okay, the voltage keeps no change. So very anyway, so hope that these two slides can help you understanding the principles of drawing the equivalent circuit for a given machine like transformers, because the mathematically, so the changing of the equivalent circuit is a little bit complicated. So they're taking time to understanding the equations, to transfer the equations using the mathematical games. But a straightforward way is that we try to make the primary and secondary from the point of view of the engineering. So we're making the primary and secondary by transformation of the parameters, making the primary and secondary has the same voltage, same currents, so that they can touch together safely. So this is a straightforward way. Meanwhile, we follow the rules that the Ohm's law. We follow the rules of the power conservation law. That's straightforward. Okay, so this is the equivalent circuit for the transformers, which will be frequently used in the next year's subject, BSc 3123. So where for power installation. Okay, anyway, so in practice, transformers, as we just show you that, so they have the reading resistance, they have leakage reactance. They have R losses. That's the difference. So the R losses they have due to the excitations, where transformer excited by an AC source, but with no load at the secondary, they still have small currents and the primary is observed. So because they need some magnetic flux produced inside the core, so that they make the primary and secondary linked together. So primary secondary coupled because there are magnetic field between each others. But in the magnetic field produced by currents. So no currents, no magnetic field. No magnetic field, no coupling between the primary and secondary. So then the primary will be short circuit. Imagine, So because the primary, secondary electrically isolated, magnetically coupled. So primary supposed to be supplied with a voltage 20 volts voltage, and secondary is open. If there is no magnetic field flux, link the primary and secondary, making the secondary impedance be linked to the primary. Then the primary impedance will be very small. And primary, like a short circuit. That's terrible. Luckily, of course, we are using the magnetic field, to coupling between the secondary and primary. So because when we will have the core materials there. When we have a small current go through the primary, there is a magnetic field produced. Once this magnetic field produced, this magnetic field will come to the secondary. And the secondary will induce voltage. The stronger magnetic field, the stronger voltage. So the secondary induced voltage used to overcome the primary supplied voltage. Because the secondary is open, the secondary current is small, 0, and force the primary current be small because of energy issues. Okay. So anyway, the excitation branch has been described by using the core losses and mutual reactance. So here, in different books there was a different symbols, right? Here when we're using the RC, this refers to the primary, so refer to primary. So we just when it is drawn in the equivalent circuit mutual, if we say the mutual, okay, so mutual core resistance, okay, mutual core, right, reactance, okay, so we're using the mu here, M here, right, mutual, M here. But you know the relationship between where we refer, okay. When referred to primary, I am still referred to the core losses, and the X mutual will be transferred into XMP. When referred to secondary, so the mutual branch reactance actually, okay, so and the mutual one actually, okay, becomes the XM secondary. XM secondary. That's the difference. Okay, that's the difference. So the secondary, right, refer to if the refer to primary, that keeps this to keep the primary values. Refer to secondary, but if you still using the RC, that's referred to primary, then in the secondary actually it should be like this. Okay. Oh, sorry. Okay. So that's okay. When you see some symbols at different places, they may start to different. Okay. So that's the meaning of it. That's the meaning of it. A last point is that the per unit systems, okay, that means we're using the ratings of the transformers as the base space of the unit to describe the systems. A typical usage of it that we usually describe the internal impedance of the transformer as the percentage of the base values. For a given transformers, for the primary its base values, for the secondary its base values. They are different. Primary base impedance is the primary rating voltage over primary rating currents. And the base impedance also is the primary base voltage square over the total rating powers. Similarly, the secondary base impedance is the secondary base voltage over secondary base currents, or the secondary base voltage over the total power ratings. The powers for primary, secondary, the base values the same. This one, and the internal impedance usually be described as the percentage of the base values. So when we're talking about the internal impedance, that means the transformer primary resistance, primary secondary resistance, primary leakage reactance, secondary leakage reactance, right? Okay. The point is that, so for the transformer, the internal impedance is usually expressed in the percentage of the base impedance. Remember this one. So when you use the impedance of the internal impedance to explain, to calculate some internal voltage drops, to explain the internal power losses, you should transfer these values from the percentage of the base values into the actual values. Okay, so you know how to transfer it from the percentage into the real values in unit rho. And we have to write testings. So the so-called open circuit tests, the procedures, and the purpose of it. Okay, actually, so this has been examined in the final examination to recall your memories of it. So open circuit tests usually has been carried out, and one side of the transformer usually actually low voltage side of transformer, with the high voltage side be opened and monitored with ammeter with voltmeters. And the low voltage side, we can using a low voltage source with the rating voltage applied to the low voltage side. And we monitor the input voltage and currents. So of course, at the beginning, making the voltage be 0, and then increase the voltage gradually to the rating voltage. Okay, so we monitor the input voltage and output voltage, input currents, and input powers. As such, the input powers will reflect the core losses of the transformer at rating voltage. The input voltage over the output voltage will represent the general transformer ratio of this transformer. And the input currents represent the excitation branch current when it is opened. With these measurements, one can determine, one, the core losses and rating voltage. Two, that the core losses equivalent resistance RC, referred to the lower side. And then the input voltage over the input currents that giving the input impedance, which is dominant, not exactly, dominant by the excitation branch impedance in series. So here is series equivalent of the refer to primary. Series equivalent refer to low voltage side, this side. This side, and you can change it into the parallel expressions. Okay, so that's the procedures and purpose of it. Now, the short circuits generally, so the short circuit means that for the transformer, we short circuit one side of it. Generally, is the a low voltage side of it, and with the another side, generally is the high voltage side of it. Apply with a small portion of the rating voltage, so that the systems has the rating current for all of it. We modulate the input voltage, which should be a small portion of the rating voltage, and the input current, which should be the rating currents. And the secondary currents will also be the rating current as secondary. The input powers then will represent the internal copper losses, because the input voltage is small portion of the rating voltage. The input, the core losses across the transformers is much smaller than it at the rating voltage. So it can be ignored. Of course, right, at the beginning, you have to, right, making the voltage be zero, then gradually increase the voltage from 0 up to certain levels. Generally, 5 to 10% of the rating voltage, so that the input current be the rating currents. Then you can go to the full load, copper losses. You got full load copper losses of the transformer. You can estimate the internal resistance of the transformer, refer to the, for example, high voltage side. And also, you can find out the equivalent internal impedance of the transformer, refer to the high voltage side. Of course, you can change it into refer to secondary. Refer to secondary. So that's the, based on the short circuit, you can go to write the internal impedance of the transformer, and the copper losses of the transformer and the rating currents. Combine the open circuit and short circuit, one can estimate the transformer's efficiency, and different, right, loading levels, full load levels, half load levels, and around 20% of the full load levels. Meanwhile, if you have, since you have the internal impedance of the transformer, you can furthermore to estimate the transformers, voltage regulations, and so on. Okay, so here is the efficiency calculation formulas. So one formulas of it. Okay, you can write using different way. And volume regulations definitions of it. Furthermore, okay, so if you know the internal impedance of the transformer, refer to the secondary. If you know the secondary rating output voltage and the different loading impedance, different loading power factors, you can estimate the voltage regulations based on such simple calculations. Okay, so I think because this formulas is based on the complex number form analysis of the phasor diagrams, or we say it is based on the internal equivalent circuit of transformers. Okay, you can prove it easily. I'm not explain it in detail at this moment of it. Okay, so this is thorough revisions on the single phase transformer, including its principle, its structure, its principle, its equivalent circuit, its testing, and its analysis. So in the exercise books, we have several examples on it, and we will discuss on it in detail during the coming tutorial sessions, so that you have a good understanding on the concepts and principles we learned today. So that's the end of today's lectures, which is our revisions on the single-phase transformer. Next lecture, we'll talk about the three-phase transformer and focus on the difference between the three-phase and the single-phase one. See you next time. Goodbye.